Hello. Today I'm going to be talking to you about our paper, Contention Resolution Without Collision Detection. I'm Bill Kuzmal, and this is joint work with Michael Bender, Zvi Kopelowitz, and Seth Petty. The contention resolution problem takes place on what's known as a shared channel, sometimes also called a multiple axis channel. In each step on a shared channel, any players that are present can choose to either attempt to broadcast during that step or to not attempt to broadcast. If more than one player attempts to broadcast on a given step, then the attempts collide with one another and no successful broadcast occurs. On the other hand, if exactly one player attempts to broadcast on a given step, then you get a successful broadcast. In this example, where the x-axis is the step number and the y-axis is the number of broadcast attempts on each step, we have two steps where there are successful broadcasts, because these are the steps where exactly one player attempted to broadcast. The notion of a shared channel models situations such as, for example, the Ethernet, where Ethernet connections, where you have a single cable acting as a shared resource for players or processors, and the processors want to all communicate over that shared resource. The channel also gives feedback to the players in the form of binary feedback, ones and zeros. At the end of each step, all of the players in the system receive either a 1, indicating that there was a successful broadcast during that step, or a 0, indicating that there wasn't a successful broadcast during that step. In the example from the previous slides, the players receive a 1 on steps 1 and 4 because those are the steps with successful broadcasts. One of the most fundamental questions that you can ask about a shared channel is the contention resolution problem. Here you have players arriving over time, so the players don't necessarily arrive all at the beginning of the game. And each of the players wishes to successfully broadcast once. You can think of each player as having a message that they want to send on the channel. The goal is for the players to somehow work together in order to make good use of the channel. Roughly speaking, what that means is you want a constant fraction of the steps to have successful broadcasts. You want the channel to achieve high throughput. The question that we're going to be asking today in this talk is, can one design an algorithm that achieves constant throughput for this problem? And the answer is going to turn out to be yes. Now, in order to describe this problem, the contention resolution problem, in a little bit more detail, let me describe it to you again, except this time from the perspective of an individual player. The player arrives at some point in time, and from the player's perspective, that's time 0. So the player has a local clock. There's no shared global clock. Each step that the player's in the system, the player can choose to either attempt to broadcast or not to. And then once the player finally successfully broadcasts, that's when the player leaves the system. So that marks the end of the player's lifetime. The goal, again, is for the players to work together in order to achieve constant throughput. So in order to make good use of the channel. The problem of contention resolution has received a lot of attention over the years. And the state-of-the-art algorithms for contention resolution, what they do is they assume an extra form of feedback known as collision detection. What that means is that at each step, the players are told not only a 1 or a 0, saying whether or not the step had a successful broadcast or not, but the players are also told whenever there's a step that has a collision, which means that multiple broadcast attempts occurred and they collided with one another. This allows for players to distinguish between steps that failed due to too many broadcast attempts versus steps that have failed due to no broadcast attempts occurring. Using collision detection, there's a very natural approach that players can take. They maintain a broadcast probability for each step. And whenever the player sees a step that contains a collision, the player lowers their broadcast probability because they know the channel is oversaturated. On the other hand, whenever the player sees an empty step, a step where there were no attempts made, the player increases their broadcast probability because they know the channel is undersaturated. It turns out that you can actually make this approach work. And what past researchers proved is that using collision detection as a tool, one can design algorithms for contention resolution that achieve constant throughput. And so the question that we're going to be focusing on today in this talk is, what if you don't have collision detection? Can you still achieve constant throughput? If you don't have collision detection, then there's no known algorithms that have good theoretical guarantees. But there is an algorithm that's used widely in practice, namely exponential backoff. There are lots of ways to think about exponential backoff, but for the purposes of this talk, we're going to use one that's a little non-standard. For the purposes of this talk, we're going to say that what exponential backoff does is that at time t, the player broadcasts with probability 1 over t. That's exponential backoff. And of course, the upside of exponential backoff is that it's used widely in practice. It's used in a lot of real-world systems. On the other hand, exponential backoff has poor theoretical performance. In general, it doesn't achieve anywhere near constant throughput. In order to motivate the algorithm that we're going to be describing today, I want to describe to you what the two main problems are that exponential backoff has. The first problem with exponential backoff is what we're going to call the Stragglers problem. And to see this problem in action, suppose we just have n players arriving at the start of time in a batch. In some sense, this is actually the best case scenario for exponential backoff. Because what happens is that between steps n over 2 and n, the players are always broadcasting with probability order 1 over n. And so during those steps, we actually have a lot of successes. We actually get order n successes during those steps. On the other hand, what ends up happening is that the stragglers, which is to say the final players to succeed out of all the n players, end up taking a long time to succeed. They end up requiring time n polylog n. That's the stragglers problem. And this problem will end up being important later in the talk when we end up facing a similar problem in our algorithm. But it turns out that the stragglers problem isn't actually the main problem that exponential backoff has. The main problem is the problem of contention. And in order to see this in action, suppose that in addition to having the n players arriving at the start in a batch, suppose that additionally we have a new player arriving every order 1 steps. And what happens now is that exponential backoff actually does very badly. In fact, almost all of the steps fail to have a successful broadcast. You have almost no successful broadcasts. And the reason that this happens, it turns out, is high contention. So what you can show if you analyze this situation is you can show that on every single step, the expected number of players that attempt to broadcast during that step is at least logarithmic. And that means that with the vast majority of the time, you're going to have collisions during that step. You're not going to have a successful broadcast. That's the contention problem. Okay, so far I've been describing to you what are the problems with exponential backoff. In the rest of the talk, I want to describe to you our algorithm for the contention resolution problem. And to start off with, I want to describe to you a setting where exponential backoff actually does very well. And then what we're going to do is we're going to describe an algorithmic mechanism for reducing the problem of contention resolution to this new, simpler setting where exponential backoff does well. And then finally, at the end of the talk, we're going to come back and handle the problem of stragglers. That's the outline of the rest of the talk. Okay, so to start off with, a setting where exponential backoff does very well. It turns out one thing that exponential backoff is good at is getting a single success. So imagine that we have order n players arriving into the system over time. But now our goal isn't to achieve high throughput. Our goal is just to have at least one success by time order n. That's our goal. And now it turns out exponential backoff actually does very, very well. And so for example, in the setting that we described before, where exponential backoff did badly because of contention, exponential backoff does well at achieving a single success. And intuitively, the reason for that is, and you can show this, is that even though there's high contention on each of the steps individually, if you look at all of the steps together, there's a good shot still that at least one of them successfully broadcasts. So exponential backoff is really good at getting a first success. And one consequence of this is that exponential backoff is also really good at what we're going to call the simplified contention resolution problem. So this is a simplified version of contention resolution that has been carefully designed so that exponential backoff will do well at it. And in this version of the problem, we have two types of players. There's the players that we're going to call batch players. These are the players that arrive in a batch at the start of the game. And these players they all want to have a successful broadcast, just like in standard contention resolution. But then there's also the other players, the players that arrive after time zero. We call these players the fresh arrivals. And these players leave the system as soon as they see any success, even if it's not their own success. It turns out what you can show is that if all of the players, both the batch players and the fresh arrivals, use exponential backoff, then exponential backoff in some sense does quite well at simplified contention resolution. So for example, in the setting before where exponential backoff did poorly, we now end up having order n successes during steps n over 2 to n. And in fact, you end up having theta n successes. Now, you still have the problem of stragglers. So we haven't solved that problem, but I want to mostly ignore that until the end of the talk, and then we'll come back and handle it at the end. And so, in some sense, exponential backoff does really good at this simplified contention resolution problem. And our goal is going to be to reduce the standard contention resolution problem to this simpler problem. And so since we're going to be talking about simplified contention resolution quite a lot in the rest of the talk, I want to introduce two terms for thinking about it. We're going to say that the batch players, the players that arrive at the start, we're going to say that those are, quote, participating in a batch protocol. And then we're going to say that the players that arrive later on, the fresh arrivals, we're going to say that those players are, quote, interfering with the batch protocol. Okay, so our next goal is to try to reduce the problem of contention resolution to this simpler setting, simplified contention resolution, in which we know exponential backoff does well. And so now I can describe to you our algorithm. Our algorithm thinks of there as being two channels. So we treat the odd numbered steps as being one channel, and we treat the even numbered steps as being a separate channel. Now, the players don't know which are the odd steps versus which are the even steps because there's no shared global clock. But the players do know that we're treating one parity of steps as being one channel and the other parity as being the other channel. At any given moment, these two channels are going to serve separate roles from one another. One of the channels is going to act as what we're going to call the active channel, and that means we're going to be running a batch protocol on it. In other words, we're going to be running an instance of simplified contention resolution on the active channel. The other channel is going to be the silent channel. It's not going to contain any successful broadcasts, and we'll see why that's important in a minute. What's going to happen is every once in a while, these two channels are going to swap roles with one another. So the active channel will become silent, the silent channel will become active, and they'll oscillate in their roles over time. That's going to be the overall structure of our algorithm. So you can think of every time that the channels swap roles, you can think of that as representing the beginning of a new phase for our algorithm. And roughly speaking, what's going to happen during a given phase is the following. The players that arrived during the previous phase are now going to act as batch players on the active channel. They're going to be batch players in the instance of simplified contention resolution that happens during this phase. And then the players that arrive as new arrivals during this phase, they're going to act as the fresh arrivals in the simplified contention resolution problem. And so they're going to have to make sure they don't interfere too much with what's going on the active channel. Additionally, these new arrivals have to figure out when the phase ends. That way, at the beginning of the next phase, they can join the active channel as batch players. That's the basic structure of the algorithm. And now let's dive into detail to see how it works. Okay, so to start with, what do the batch players do? The players that are the batch players on the active channel in a given phase. Well, because they're in an instance of simplified contention resolution on the active channel, they perform exponential backoff on the active channel, hoping to get a success. But additionally, these players also actively jam the silent channel by always broadcasting on it on every step. And what that means is that because these players are broadcasting on the silent channel on every step, that's going to always cause collisions. And that's what ends up keeping the silent channel silent. So that's what the batch players do. Now let's look at what happens when a player freshly arrives into the system, when they're a new arrival. When the player first arrives, they don't know which channel's which. They don't know which channel is active and which channel is silent. What the player does is they perform exponential backoff on both channels until eventually they see a success on one of the two channels. And here's where it's important that the silent channel is silent. Because what we can learn from the success is that the channel on which the success occurred must be the active channel. Now the player knows which channel is the active channel. By the way, it's tempting to just not do anything, to not attempt broadcasts at all until we see a first success. But we can't afford to do that. Because as far as the player knows, it might be that the only players in the system are brand new arrivals, just like this player. And so if everyone just waits around until they eventually see a success, then nothing will ever happen. That's why we have to perform exponential backoff until we see a first success. Now, once the player sees a success on the active channel, what they do is they stop making any broadcast attempts in the active channel. They stop interfering with the active channel. And this is important because this is what makes it so that what's occurring on the active channel really is an instance of simplified contention resolution. That is, the fresh arrivals leave the channel as soon as they see any successes. On the other hand, what the player does continue to do is the player continues to perform exponential backoff on the silent channel. And the player continues to do that until eventually they see a successful broadcast on the silent channel. Now, how can a successful broadcast on the silent channel occur? Well, usually what's happening is the players on the active channel are jamming the silent channel, keeping it silent. What a successful broadcast on the silent channel means is that all the players on the active channel must have left the system. They must have all succeeded. And so when we see a success on the silent channel, we enter a new phase, and the two channels swap roles with one another. Okay, so we've entered a new phase. All the players on the active channel in the previous phase have succeeded. Now the channels have swapped roles. And now what happens is that all of the players that were performing exponential backoff on the silent channel in the previous phase now join as batch players on the active channel in the new instance of simplified contention resolution that takes place in the new phase. And so that's how we enter a new phase. And so to put the pieces together, what's happening is that during each phase, the players that arrived during the previous phase are now batch players on the active channel in the current phase. And the players that are in the active channel in a given phase actively jam the silent channel in order to keep it silent throughout that phase. That means that when a success finally does occur in the silent channel, it can indicate the end of the phase. And then finally, all of the new arrivals during a given phase are careful to make sure that they only interact with the active channel until they see a first success. And that's what makes it so that what's occurring on the active channel is an instance of simplified contention resolution, which we know exponential backoff does a good job at. That's the overarching picture of the algorithm. It turns out if you want to analyze this algorithm, there's a whole bunch of interesting phenomena that arise. But one of the biggest problems you face is the problem of stragglers, which we talked about before. In particular, remember that even though exponential backoff does a good job at getting a lot of successes in the simplified contention resolution problem, we still have stragglers, which is to say that the final players to succeed still take a very long time. And the result is that each phase in our algorithm takes too long. We don't get good throughput. The solution that we have in the paper is we modify our algorithm so that when players are jamming the silent channel, they jam the silent channel probabilistically, which is to say that rather than always jamming the channel in every step, they actually perform a form of exponential backoff on that channel in order to try to jam it probabilistically. The result is that the silent channel is jammed for a while, but then once the active channel starts to thin out, meaning that roughly speaking, a constant fraction of the players on the active channel have succeeded, then the probabilistic jamming on the silent channel ends up failing. And now the channels get to swap roles without stragglers being a problem. That's how we solve the stragglers problem. If you analyze the algorithm, then what you get is an algorithm for contention resolution that achieves constant throughput, and that also has the property that it's energy efficient in the sense that the average number of broadcast attempts made by the average player is only polylog n. And I want to conclude the talk by pointing out one property of the algorithm that I think is kind of surprising, which is that the players are always performing a form of exponential backoff at any given moment. And so at any given moment, the players are using an algorithm that doesn't work well in general. But by just introducing a few simple rules for deciding when a player is performing backoff on which channels, we can transform this algorithm that doesn't work into a new algorithm that does and always gets constant throughput. That's our main result. Thank you very much.